So friends, next factor that will affect the efficiency of ASC or pressurized solvent extraction is the solvent to feed ratio. That is, for a given amount of the matrix or the sample, how much solvent we should use for its extraction. And it has been observed that this ratio or the amount of the solvent that is used to extract a given amount of the sample will also govern the overall extraction yield or the extraction efficiency. Vis-a-vis, it will also govern the cost of overall extraction process. Now it depends in case of accelerated or solvent extraction or pressurized solvent extraction, solvent to feed ratio largely depends on the mode of this extraction technique. Whether you are using a static mode or you are using a dynamic mode, that will help you in optimizing the solvent to feed ratio. If you are using a static mode, then it has been found that 1:3 or 1:15 solvent to feed ratio is the most optimum one. That is, for 1 gram of sample, either you extract with 3 ml or 15 ml of the solvent. It has also been found that if you increase the number of cycles without changing the solvent to feed ratio, that has given more efficient results or better result in terms of the overall yield of the extraction process. Say for example, we are extracting 1 gram of drug, and depending upon the nature of our sample, depending upon the solubility characteristics of our solute, we decided that we should use 15 ml of solvent. That is, feed to solvent ratio is 1:15. Now, rather than using 15 ml of the solvent in one go or in one cycle, I will divide this 15 ml into 3 cycles of 5 ml each. So I will extract this 1 gram of drug by 5 ml of solvent 3 times, and each time I will be using fresh 5 ml of the solvent. Now, what is the significance of breaking this 15 ml into 3 5 ml portions? Because we are extracting the drug in each cycle with fresh solvent, and when your drug is coming in contact with the fresh solvent, every time the shifting of equilibrium takes place, the concentration gradient is always there, and the solutes are easily extracted out into the solvent. Because every time fresh solvent is coming, so the chances of attaining equilibrium between the concentration of solute in solvent vis-a-vis the concentration of solute in the matrix are very less, and therefore whenever you are treating large amount of solvent, whenever you have to use a large amount of solvent, it's always better to split the entire volume of the solvent into different extraction cycles. This is one aspect. Second, we can also decrease the ratio of feed to solvent by increasing the number of cycles. This helps in reducing the overall solvent consumption of the extraction process, during the extraction process. So I will again go back to the same example wherein I have to extract 1 gram of drug, and we selected 15 ml of the solvent that has to be used to extract 1 gram of drug. So in the previous example, I divided 15 ml of solvent into 3 equal portions of 5 ml each. Whereas in the second scenario, as I told you, we can also decrease this ratio in the subsequent cycles. So in this case, I will decrease the ratio. So in the first cycle, I will be extracting 1 gram of the drug with 5 ml of the solvent. Then in the second cycle, I will extracting 1 gram of drug with say 3 ml or 4 ml of solvent. And in the last or the third cycle, I will extract the same 1 gram of drug with say 3 ml of the solvent. So if we total up the volume of the solvent used in this manner is 5 plus 4 plus 3, that is 12 ml of solvent. So we are further decreasing the volume of the solvent. And it has been observed that by decreasing the ratio in each cycle does not impact the overall extraction efficiency in comparison to if you are having the same portions of the solvent, same volume portions of the solvent. So this is another example by which you can manipulate, you can optimize your extraction process in terms of solvent to feed ratio or feed to solvent ratio. But yes, if you are using large amount of solvent for very small amount of drug, you are increasing the overall cost of the extraction process in terms of the cost of the solvent as well as the energy that is required to extract out by using large volume of solvent. On the other hand, if you are using very less amount of solvent, then you will not be able to extract out the solute molecule, desirable amount of the solute molecules from the matrix, which will also add up to the overall cost of the process. Now the second mode is the dynamic mode, and we know that in dynamic mode solvent continuously flows through the extraction cell coming in contact with the drug, and therefore the flow rate of the solvent that will govern the volume of the solvent that has to be used in the dynamic mode. Now if we increase the flow rate, obviously the solubility of the solutes will increase and it will also increase the mass transfer. But again, we have to keep in mind the overall cost that will be involved in increasing the flow rate, because once you increase the flow rate, the amount of the solvent that has to be used for the extraction process will tremendously increase. The volume of the solvent that has to be used will tremendously increase. Now it has been found that the extraction rate does not increases whenever you increase the flow rate if diffusion of the solvent into the matrix is the main rate limiting step. Say for example, if we are using a particular solvent and in a dynamic mode for extracting solute from a given sample, then if diffusion is the major bottleneck in the overall extraction process or extraction efficiency, then by increasing the flow rate of the solvent will not help in increasing the extraction yield. Whereas if diffusion is the rate limiting step and you increase the temperature, and by increasing the temperature we have discussed that when we increase the temperature the viscosity of the solvent decreases, and once the viscosity decreases its diffusion increases. So by increasing the temperature we can enhance the extraction rate, but by increasing the flow rate we cannot enhance the extraction rate if diffusion is the main rate limiting step in the extraction process. Whereas if solubility of the constituents, solubility of the solute is the major rate limiting factor in the extraction process, then yes, increasing the flow rate will increase the amount of the solute that are extracted during the process. So in simple words, if I say if diffusion is the rate limiting factor, then we should not increase the flow rate, but we should increase the temperature. If solubility is the rate limiting factor, then we should increase the flow rate, and in such conditions increase in temperature will not affect the extraction efficiency. In general, it has been observed that for a sample range of 1 to 5 grams, flow rate of 0.5 to 3 ml per minute is normally used in the dynamic modes. And if we further decrease the flow rate below the 0.5 ml per minute rate, then I'll go back to that instrumentation aspect wherein I discuss about the pressure restrictors that are being used during the dynamic mode, which help in maintaining the pressure of the solvent flow. So if we are using dynamic mode and we are using a flow rate of less than 0.5 ml per minute, such a flow rate can cause damage to those pressure restrictors and overall process can become non-uniform. Whereas if you increase the flow rate above 3 ml per minute, then because large amount of solvent will be used, and such large amount of solvent will cause the dilution of the extract. So therefore one has to optimize the proper flow rate of the solvent whenever you are going for the dynamic mode. And static mode we have already discussed, 1:3 or 1:15 is the optimum ratio. Now we move on to the sample or the matrix related factors, and it has been observed that whether it is the particle size, whether it is the age of the sample, whether it is the form of the sample from which the solutes have to be extracted, such kind of characters of the sample, they affect the overall extraction efficiency. Say for example, you are extracting a sample wherein the desirable secondary metabolites are in more or in high concentration when the sample age is young, and you are using young sample, then obviously you will get good amount of the secondary metabolite, desired secondary metabolite. Whereas if you are using an aged sample or old sample, then obviously the yield will decrease. So the sample quality also governs or also affects the overall extraction efficiency. Then the next factor I discussed was the type of the sample or the type of the matrix which we are using to extract the secondary metabolites or the solute molecules. So for example, if we have to extract phenolic compounds from olive leaves, then 140 degrees temperature has been found to be optimum to extract out maximum phenolic compounds. Whereas if we are using olive pomace, which is nothing but the extracted pulp of the olive fruits, then we require at least 200 degrees Celsius of temperature to extract out the phenolic compounds. So this was just one example how by changing the characters of the matrix, the temperature conditions are changed. Vis-a-vis temperature, obviously we have to change the pressure conditions as well. Next matrix factor is the particle size, and till now whatever extraction techniques we have discussed, we have found by decreasing the particle size, the overall extraction efficiency increases, but again up to a particular level. Now the particle size has been found responsible for the mass transfer mechanism, or I'll say the influence of particle size largely depends upon the mechanism by which solutes are being transferred into the solvent. So if the mechanism of this mass transfer is diffusion, then it has been found the overall extraction efficiency increases with the decrease in the particle size, but again up to a specific limit. And if we further decrease the particle size below that limit, then obviously extraction efficiency decrease. There can be n number of the reasons, like there can be certain technical difficulties in the extraction cell or the extraction unit which we are using, or by decreasing the particle size beyond the prescribed limit, beyond the optimum limit, that will lead to the formation of a very compact matrix bed or the sample bed in the extraction cell, which will further increase the back pressure of the solvent, thereby causing an overload onto your system. Then that compact bed does not allow solvent to enter into each and every corner of that extraction, that sample bed that has been formed in the extraction cell. So such kind of condition also lead to non-uniform extraction of the sample. So these are few examples what technical difficulties can come whenever you decrease the particle size below a specific limit. And it has been found that the common particle size that is being used in accelerated solvent extraction or pressurized solvent extraction is somewhat below 4 millimeters, 0.4 millimeters. Now there are obvious advantages of decreasing particle size, because as you decrease the particle size, it will help in easy diffusing out of the solute molecules from the matrix. Decrease particle size, increase the surface area. We all know that by decreasing the particle size we increase the surface area, and as we increase the surface area, it improves the contact of that sample with the solvent. So now more solute particles, more sample particles will come in contact with the solvent. Further, when we decrease the particle size, we are decreasing the depth of the solvent penetration. So if we are using, say, a particle size of 4 millimeter of the drug of the sample, then solvent has a depth of penetration of 4 millimeters, say for example. Now solvent has to enter in a 4 millimeter distance into the matrix to solubilize the solute. Whereas if we decrease the particle size to 1 millimeter, now in this case solvent has to enter to a depth of 1 millimeter only to solubilize the solute molecules. So this is how the reduction in the particle size decreases the penetration depth for the solvent, thereby increasing the overall extraction efficiency. Next factor that will affect the efficiency is the time of extraction. Again, this time of extraction is critical because it impacts the efficiency, it impacts the yield that is obtained, vis-a-vis it will also govern the cost of the overall extraction process. And the extraction time largely depends upon the physical nature of your sample, whether the sample is soft, whether the sample is hard, whether the sample is in liquid form or in the semi-solid form. So obviously for soft samples we require lesser extraction time, for harder samples we require larger or the longer extraction durations. Then type of solvent that you are using will also govern the extraction time. Many times it happens we have to use a solvent which has a limited solubilizing power for that particular solute for say n number of technical reasons. In such cases where the solvent is having limited solubilizing power, obviously the extraction time increases. We have to allow solvent to remain in contact with the sample for longer duration in order to have a better yield. And it has been found whenever you are using a static mode of ASC or PSC, then 15 to 20 minutes for a normal kind of sample has been found sufficient. Whereas for complex mixtures of different samples or for hard samples, 30 to 60 minutes have been found most optimum for static mode. And in case of dynamic mode, where solvent is continuously flowing through the extraction cell, 50 to 30 minutes for normal sample, and for complex mixture or harder samples, longer durations are required, and these longer duration or the time duration will also depend upon the flow rate of the solvent that is being used in the dynamic mode. Now we move on to the hyphenations of pressurized solvent extraction or the modifications of pressurized solvent extraction. And one such example is the combination of pressurized solvent extraction with the ultrasound assisted extraction. And I'll again go back to the instrumentation aspect of PSC, wherein we discussed the extraction cell is placed in a thermostated unit to maintain the required temperature conditions. In case of PSC plus UAE technique, that is pressurized solvent extraction along with UAE, that thermostated unit is nothing but your ultrasound assisted unit. So in this example, the aliphatic diesel compound or organics were extracted from a given sample or from the soil along with the polycyclic aromatic hydrocarbons. A pressure of 1800 psi was used and dichloromethane was solvent, and the entire extraction process was carried out for 10 minutes. Whereas after optimizing, it was found that extraction time of 20 minutes was the most optimum one, and a combination of dichloromethane along with acetone in 1:1 ratio was most appropriate solvent combination for extracting out the maximum components. So in this figure you can clearly see the flow diagram of ASC along with ultrasound assisted extraction. So you can see there is a solvent reservoir which is attached to a pump, a high pressure pump to pump the solvent into the extraction cell, and these pumps take the solvent into the thermostated unit, which is nothing but an ultrasound bath, or in simple cases we can use a oven also. So since we are talking about the hyphenation of PSC, here we have ultrasound bath. Now this solvent is passed through I will say into a preheated coil where the temperature of the solvent is slightly increased, and then it enters into the extraction cell, and this whole unit is enclosed in an ultrasonication bath which produces the ultrasounds. And in my previous lectures I have discussed that how ultrasound increase the extraction efficiency. So here we are combining the pressurized solvent extraction and ultrasound assisted extraction. So once the extraction is complete, the solvent or the extract is passed through a cooling mechanism, and then it is entered into the collecting vial. If we are using a dynamic mode, then obviously there is another valve that is placed between the collecting vial and the cooling bath. So accordingly we open and close the valves in order to get our extract. Next combination is the combination of accelerated solvent extraction along with solid phase extraction, and to these extraction units an analytical equipment has been attached, that is gas chromatographic and MS, that is mass spectrophotometry analysis. So after extracting the components, you can directly analyze the samples also, and in a study 7 compounds which are normally phthalates that are found in soil were used to extract from the given sample of the soil by using this technique. So you can see the list of the 7 phthalates that were extracted from the soil sample using this technique. So what happened was a tri-solvent mixture was used as an extraction solvent, which was comprised of ethyl acetate, hexane and dichloromethane in a ratio of 2:3:2. The overall extraction time was set for 15 minutes and static mode was used in ASE. Now once the extraction was complete, the extract was passed on to solid phase extraction column where the purification of extract occur. So once the extract was loaded onto SPE column, that is solid phase extraction column, and the output of this SPE column was further subjected to gas chromatographic analysis. So this is how one can always go for hyphenations. This is the beauty of the modern techniques, that we can combine 2 extraction techniques. We can hyphenate these extraction techniques by incorporating modern sophisticated analytical equipments with them in order to save the labor, in order to save the overall time to analyze, to extract these solute molecules. Now we move on to the last aspect of PSC, that is the applications. And since we are mainly concerned with the extraction aspect, the PSC technique has been used to extract various types of secondary and the primary metabolites from different types of matrix. It has been used to extract lipids such as phospholipids from various food matrices like soybean, egg yolk, calf brain, and from the liver of certain animals also. Various bioactive compounds like fatty acids, saponins, or the lipid soluble compounds like lipid soluble vitamins are there, terpenoids are there, or steroidal compounds which are again lipophilic compounds. They have also been extracted using accelerated solvent extraction technique. It has also been found that we not only extract the non-volatile compounds, but we can also extract volatile compounds from the plant matrix using accelerated or pressurized solvent extraction. Various volatile compounds along with essential oils have been extracted from different samples like fruits, woods, leaves, or entire herbs have also been used. Apart from extracting these compounds, various studies have been mentioned wherein they compared the results of the extraction techniques, different extraction techniques used to extract these volatile compounds. And this comparison has been made both in terms of analytical comparison and also in terms of the biological activity comparison. So I have taken one example wherein Tam et al. They extracted essential oils from the fruits of Cyprus rotundus, and they utilized 3 different extraction techniques. One is hydrodistillation, which is a conventional technique to extract volatile oil. Second is supercritical fluid extraction, which is again a modern technique. And third was accelerated solvent extraction technique, which we are discussing right now. And when they extract the volatile oil and they analyze the oil, they found the oil that was extracted using ASC was having maximum component of the terpenoidal compounds like copain, cyprine, selenine, cypron, and alpha and beta cypron. And not only this is just an example of the analytical comparison. Various studies in the literature have been mentioned wherein the antioxidant potential of the secondary metabolites have been analyzed when they were extracted by using different extraction technique. Say for example, various studies you will find in literature wherein various polyphenolic compounds, specifically flavonoids, have been extracted by using different extraction technique like soxalate extraction, accelerated solvent extraction, supercritical fluid extraction, or maceration. And it has been found the flavonoids that have been extracted by using accelerated solvent extraction, they retain the antioxidant potential, or I will say the antioxidant potential of the flavonoids extracted by ASC was much higher in comparison to the flavonoids that were extracted by using other extraction techniques. And not only the secondary metabolites, in food industry also it has been found that the flavor components or the color components which have been extracted by using ASE, they retain the color or the fragrance at the highest level closest towards the natural odor or the natural color of those compounds. As I discussed, that various polyphenolic compounds have also been isolated or extracted rather using this ASE. We have, you will find studies related to extraction of flavonoids or their glycosides, extraction of the anthocyanins, which are the pigments responsible for coloring of the plants. Then tannins are there, coumarins are there, lignans are there, and various other glycosides. Then ASE is also used in food industry to extract out various additives. Not only additives but flavor compounds. You want to extract colorants from the food material, you can use ASE to extract coloring material from the food materials. Apart from these useful compounds, we can also use ASE to extract out various toxic compounds like pesticides. So if you want to determine the pesticidal content in a given food item, we can use accelerated solvent extraction technique to extract out those pesticidal compounds, which can be, and this technique, as we know, can be hyphenated with analytical technique, so that extract can be directly subjected to the analytical equipment to analyze the quantity of the pesticides that are present in the sample. So friends, this was all about pressurized solvent extraction, wherein we discussed regarding the principle, regarding different modes of ASE or PSE, static and dynamic, what kind of equipments are involved in both these modes, what are the steps involved in these modes of ASEs, then what are the factors that will affect the overall extraction process, both in terms of the extraction yield as well as the cost of the extraction process. Then in the end we discuss about the applications of the pressurized solvent extraction. Thank you.